Hi guys, welcome to my YouTube channel. I'm Santosh Kumar. Today we are going to discuss most important and interesting topic, power factor, um, desired power factors and related formula calculation and some case studies and what are the advantages and causes of low power factor, how we can improve our power factor. Those aspects we'll discuss today. Let us quickly touch base the basic information of power factor. Okay, so the power factor is a cosine of an angle between voltage and current. Simply we can say like it is a phase angle difference between voltage and current. So that we called as a phi, and the cos phi is a power factor. So okay, there are four different power factor usually. Okay, so one is lagging power factor, leading power factor, unity power factor, and zero power factor. Let us quickly go through all these power factors. So what exactly it means? Okay, so let's start with lagging power factor. So any AC circuit is said to have a lagging power factor when current lags the voltage by certain angle, that is from 0 to 90 degree. So let's quickly check the uh, phasor diagram. Okay, so here you can able to see uh, so voltage waveform is and the current waveform, and current waveform is after the voltage waveform, so that is why it is lagging. Okay, so if we see it in a vector diagram, so the voltage waveform, let's consider voltage is a constant and the variable is ampere. It is lagging below the voltage, it is lagging and lagging by a certain angle phi. Okay, and then it can lag from 0 to 90 degree. Okay, so that is a cos phi. So it is a vector diagram. So usually in our all our inductive inductive circuits usually having lagging power factor. Okay, so next is on leading power factor. An AC circuit is said to have a leading power factor when current leads a voltage by a certain angle, that is from 0 to 90 degree. Let's quickly check how phasor diagram. Here you can able to see the current is before voltage. Okay, so that is why it is leading the voltage. Okay, so current is leads a voltage and that is a certain angle, that is phi. Let's quickly check how the vector diagram is. So here voltage is constant. Here the current is above the voltage. It is leading the voltage by an angle phi. It can lead up to 0 to 90 degree angle. Okay. So most of our capacitive circuit is causing leading power factor. Unity power factor. When phase angle difference between voltage and current is zero, that is when they are in phase, in line, then the power factor is unity, because there's no phase angle difference. So phi is 0, cos 0 is 1. So let us quickly see how the phasor diagram. See, the voltage and current are in same waveform, wavelength. So there is no phase angle difference between voltage and current. And in vector diagram, the voltage is constant and the current is also in the same line. There is no phase angle difference. So most of our pure resistive load, okay, where there is no inductive load for to create lagging effect, and there is no capacitive load to create leading effect. So the pure resistive load will have a unity power factor. So next is on zero power factor. Any an AC circuit in which phase angle difference between voltage and current is 90 degree, then power factor cos phi will become 90 degree, so cos phi is 0, so then power factor will become 0. So those circuit we called as a zero power factor. So in a phasor diagram you can able to see exactly um, the voltage and current. So it is either it is lag or lead, so it is exactly causing 90 degree, exactly it is. So 90 degree phase angle which is having, so that is phi value become 90, so cos phi power factor will become 0. So those kind of circuit we called as a zero power factor. So let us quickly check. So in this circuit the voltage is leading by 90 degree. Okay, so the sorry current is leading voltage by 90 degree. So most of our capacitive circuit will have a leading power factor. If pure capacitive circuit is there, so then that power factor will become 0, because there is no resistive effect, there is no inductive effect. The pure capacitor load if we provide, then the phase angle difference between voltage and current will be 90 degree lead. And second is on lag. If the pure inductive load, there's no resistive effect or there is no capacitive effect, then the current lag the voltage by 90 degree. So if the current lag by 90 degree, then phi value is 90, so cos 90 is 0. So that circuit also we call it as a zero power factor. Okay, we have finished theoretical base touch, like what is power factor and what are the different power factors. There are lagging, leading, unity, and zero power factor. Let's see what and all our building loads contains. Okay, so usually our building load is mixture of all. Okay, so it is contain resistive load like heating, lighting, heaters, etc. So resistance, okay, R denoted by R, and its unit is ohms. And we have a capacitor load as well, our capacitor bank, and some of the DC loads in labs. So that is also contains capacitive loads. So that is we expressed in XC, capacitive reactance. The unit is again ohm. And the most important is inductive loads, all our pumps, motor, chiller, elevator. So that is all the inductive reactance, okay, inductive loads. So denoted by XL, it is inductive reactance, unit is ohms. So capacitive reactance XC, the formula is 1 divided by 2 pi FC, where F is frequency and C is a uh, capacitance in Faradays, okay, and pi is a constant. So next is the inductive reactance for calculation, it is 2 pi FL. So okay, and where 2 and pi is constant and F is frequency and L is inductance measured in Henry. So it's all grouped together. We call it as a impedance Z. So what is that impedance? So impedance of a circuit is an algebraic sum of R, XC, capacitive reactance, and XL, inductive reactance. So it is an algebraic sum of R plus XL minus XC, because so XL is lagging and XC is leading, inductive. So it is mutually cancelled to each other. Whatever left, that will be added into resistance. So that we called as a impedance. So for other formula for deriving impedance is Z is equal to square root of R square plus XL minus XC whole square in terms of ohms. Impedance unit also ohms. So in our building, like we have a resistive and inductive load maximum. Okay, so that is causing a lagging power factor in our power, because of majority of our load is inductive load. So that is why in order to improve our power factor, we can't, I mean, when lagging is there, we can able to achieve uh, unity power factor as well, or if it is lagging by 0.8, 0.9, that can be improved up to unity power factor simply by adding leading power factor taking loads such as a capacitor. Okay, the capacitor drawn a leading current are partly or completely neutralize the lagging reactive component of the load. Okay, whenever the capacitive connected is exactly equivalent to our inductive load, then the lagging will leading will neutralize complete lagging effect, and our power factor will become unity. Just to show, like, it is a current waveform and it is phi 1. So if we introduce IC, then the power factor will improve to phi 2. Okay, so it is not exactly inline. Okay, so when our capacitive load is equivalent to the inductive load, how much our building inductive load is there, same much amount of capacitive load, if we capacitor banks we turn on, then the lagging effect will leading effect will neutralize all lagging effect. Then our phase angle voltage between voltage and current, there is no phase angle, it will be inline up to phi value becomes 0. So then it is said to be unity power factor. So in our building load, till unity power factor, we can neutralize the lagging effect. We have touch base with power factor and different types of power factor: lagging power factor, leading power factor, unity power factor, and zero power factor, as well as we discussed with our building loads. Okay, what and all kinds of our loads we have in our building. Okay, so let's start my favorite part, power factor formula. Okay, and calculation of desired power factor. Okay, so I'll go a little bit slow because you people really need to understand this to um, implement in your building and optimize energy consumption, and maintain your building in a desired power factor. Okay, so let's quickly start with the basic three-phase power formula. Okay, so we know three-phase power formula, P is equal to root 3 VI cos phi, and if you want to convert this formula to power factor, then power factor is equal to P divided by root 3 VI. Okay, so P is simply watts or kilowatt. Okay, and root 3 VI divided by root 3 VI. Root 3 VI, we know it is simply VAR KVA. Okay, so then our power factor formula will become cos phi is equal to kilowatt by kVA. So power factor is equal to kilowatt by kVA. Okay, so I have uploaded one more video. So the UPS backup calculation are, and uh, finding out a different rating of electrical asset. So thumb rule calculation of 1 kVA, how much ampere. So you can able to refer that video. So then we'll come to know, like, kVA is equal to root 3 V into I divided by 1000. Okay, so now in this formula, power factor cos phi is equal to kilowatt by kVA. So very important thing to note, you guys, is power factor is directly proportional to kilowatt. If you increase your power factor, it will increase your active power consumption, kilowatt. Okay, so simply if you maintain power factor, unity power factor, then your consumption will suit up. Okay, so you need to check the desired power factor of your respective site. Okay, to optimize energy consumption. And meanwhile, you need to keep an eye on kVA, maximum demand. Okay, you should not cross your billing demand. Okay, so power factor is inversely proportional to kVA. if you keep on reducing, or if your building is operating low power factor, say 0.8 to 85 or 0.89, okay, so then your maximum demand may cross billing demand, and we may ended up with paying additional demand charges to EB authority. So in both factor, you need to keep an eye. One is on kilowatt consumption, optimum kilowatt consumption at desired power factor, and our billing maximum demand should not cross billing demand. So that desired power factor we need to maintain or manage in our respective building. Okay. So for this, to achieve this, it is very important to know the desired power factor of the building. So let's take a one scenario, and with the basic information which is available in any of the building, like contract demand, billing demand, and average maximum demand, or maximum demand and power factor. Okay, let's take one example and derive. Let's say one of the building which is having contract demand of 5000 kVA and the billing demand is 85% of CD. So earlier in Karnataka, it is 75% of contract demand. So very recently, on some year or 2 years, say, it has been increased to 85% of contract demand. And let's take example, the building having 2400 kVA of maximum demand recorded, and that building is operating at power factor 0.92. Let's check in this scenario or in this parameter whether this building is working with optimum energy consumption or not. Okay, so for this, let's start with the billing demand calculation. It is 85% of contract demand. So 5000 kVA into 85, so that is 4250 kVA is our billing demand. So this is a billing demand which we need to pay as a fixed demand charges. Okay, 4000, if we say like our tariff is to HT2A1, HT2AB, 2A, 2B1. Okay, so there's a per kVA charges, demand charges. Okay, like 250 rupees, 270 rupees. Okay, so this 4250 into 250 or 270 rupees per kVA charges that we need to pay along with the bill. So that is a fixed charge whether you consume active power kilowatt or not. This is a minimum charges which we need to pay to EB authorities on a monthly basis. Okay, so in this concept, let's derive our kilowatt. Okay, we know our maximum demand is 2400 kVA, and which is operating at 0.92 power factor. So to calculate kilowatt, simply we need to kilowatt is equal to kVA into cos phi. So our maximum demand is 2400 kVA operating at 0.92. 2400 into 0.92, it is coming 2208 kilowatt or 2.2 megawatt. That's what we derive, like whenever you used to ask like what is your building capacity or building load, we used to say 2.2 megawatt, 3 megawatt. So in this calculation, the building capacity is coming around some 2.2 megawatt. Okay, so now let's move to very interesting part, desired power factor. Okay, what is this building desired power factor? So okay, desired power factor PF is equal to kilowatt by kVA. So we know the kilowatt to 2208 kilowatt. So kVA we need to take billing demand kVA. So that is 85% of contract demand. That is 4250 kVA. So 2208 into 2208 divided by 4250 kVA is equal to 0.92. 0.52 desired power factor. Okay, so which is far away from the required power factor of 0.92 or 0. Or unity power factor 99. So in this calculation we can clearly tell, because the maximum demand 2400 kVA and the contract demand is 5000 kVA, whereas it is nowhere near to the contract demand or billing demand, obviously. So it is only consuming half of its contract demand. So in this calculation we can clearly justify that. So around some 45% of contract demand, okay, that can be withdraw and surrender back to BESCOM. Okay, in case of there is no future expansion to that building has been planned, or else there is no feasibility of expansion to that plant, or from last couple of years the building demand is constant and there's no future expansion also planned, you can able to easily plan to surround around some 45% of your contract demand, since the desired power factor it's coming only 0.52. Okay, so 45% of contract demand or surrender we can plan. So this plant with this equations or parameters, it is operating poor. Okay, so let's move up further calculation part. Okay, let's think we surrenders 45% of our contract demand are back to EB. So let's derive how calculation goes. So 5000 kVA earlier contract demand, 45% of 5000 kVA is 2250 kVA that we surrender back to EB. So our new contract demand 5000 kVA minus 2250 kVA, it is 2750 kVA. So our new contract demand, our new billing demand is 85% of new contract demand. So that is 2750 kVA into 85, it is 2337 kVA is our new billing demand. Okay, so let's calculate kilowatt. It's kilowatt, we have not untouched. The building demand is 2.2 megawatt, so same kVA is our maximum demand is 2400 kVA, and we are maintaining at 0.92. So 0.92 into 2400 kVA, it is 2208 kilowatt is our building load. Okay, active load. Next, we need to calculate desired power factor in this scenario with a new billing demand. So that is desired power factor is equal to kilowatt by kVA. That is we need to take billing demand. So our kilowatt is 2208 kilowatt. So our new billing demand is 2337. Power factor is equal to kilowatt by kVA. So 2208 divided by 2337, it is coming approximate 0.944. Okay, so I have considered 0.95. Okay, so but we are managing 0.92 power factor. So now power factor need to be improved from 0.92 to 0.95 as a desired power factor. Okay, to improve this we need to, as already discussed, we need to include some reactive components like a capacitor bank to neutralize the lagging effect to improve the power factor. Let's say we have included some capacitor banks and we improved our power factor from 0.92 to 0.94 or 95. So let's say it is improved to 0.95 and 96. Okay, so then our new maximum demand will be, because kilowatt is our 2.2 megawatt plant is same, it is active load which is available in the building. So we improved our power factor from 0.92 to 0.95. Then our new maximum demand will be, like, if you want kVA in this equation. So kVA is equal to kilowatt by power factor. Simply kVA will go here, power factor will come here. kVA is equal to kilowatt by power factor. So new MD will be at 0.95, 2208 kilowatt divided by 0.95, which is 2324. By improving power factor from 0.92 to 95, 0.03 improvement in power factor, okay, which affected reduction of maximum demand from 2400 kVA to 2324, okay, which is almost equivalent to our billing demand. Okay, so it is very difficult like a month on month edge of the billing demand maintenance. Okay, so what if we improve one more point, from 0.95 to 0.96 improved, what will be our maximum demand? So our maximum demand will be 2208 kilowatt divided by 0.96, that is 2300 kVA. Again you have around some 37 kVA of buffer. So like this we can calculate our desired power factor of the building, and we need to operate in this desired power factor of the building. The energy consumption kilowatt will be optimized on a minimum level, as well as you will not cross uh, your maximum demand above the billing demand. Like I said, um, we'll be discussing on more on case study. Okay, so for better understanding, let's take one more scenario. Okay, for better understanding. So scenario two, like let's take the same example for easy calculation purpose. For this building, the contract demand is same 5000 kVA and the BD is same. Billing demand is 85% of contract demand, but the maximum demand is 3500 kVA and the building is operating at 0.89 power factor. Okay, let's calculate in this parameter this building is operating optimally. Are any chances of reducing the power consumption by surrendering contract demand, or reducing the cost by surrendering some contract demand, or reducing the kilowatt consumption by increasing power factor? Okay, so let's start calculation. Again simply we need to calculate billing demand. Okay, billing demand is 85% of CD, so 5000 kVA into 85%, it is um, 4250 kVA is our billing demand. Okay, so next is on kilowatt. So our maximum demand is 3500 kVA. Okay, so power factor is 0.89. So simply kilowatt is equal to kVA into power factor 0.3500, 5000 in 3500 into 0.89, it is 3115 kilowatt. So it is 3.1 megawatt load building. Okay, so next go to interesting part of desired power factor. So desired power factor is equal to kilowatt by kVA, so that is billing demand. So 3115 kilowatt divided by 4250 billing demand kVA is equal to 0.73 desired power factor. Okay, so in this calculation also we can easily conclude that around some 25% of contract demand can be surrendered back if future expansion is not planned or not feasible. Okay, so again let's go to further more calculation. What if we surrender 25% of our contract demand in this parameters in this building? Okay, So if we surrender 25%, so 25% of 5000 is 1150 kVA that we surrender back to EB. So then our new billing demand will be 5000 minus 1250, it is 3750 is our new contract demand. So billing demand is 85% of contract demand. So 3750 into 85%, 3188 kVA is our new billing demand. So again, our kVA is untouched. So our kilowatt is untouched. That is a building demand. kVA into power factor, 3500 maximum demand into 0 operating at 0.89 power factor, that is 3115 kilowatt is our building load, active load. Our desired power factor will be kilowatt divided by new billing demand, so that is 3188. So 3115 kilowatt divided by 3188 kVA new billing demand, it is coming 0.98. So but we are operating at 0.89 power factor. What if we improve power factor from 0.89 to 0.98 and 1? What will happen? So because our kilowatt is constant, that is a building demand, building load, which need to suffice. Okay, so increase in power factor will reduce the maximum demand because power factor is inversely proportional to kVA. Okay, so our new maximum demand in kVA is 3150 kilowatt divided by improved power factor 0.89. It is 3178 kVA is our new maximum demand. Okay, which is almost equivalent to our billing demand. So if you want to keep a buffer in billing demand 10%, 50%, you can always go for higher power factor in this scenario. So if we maintain unity power factor, okay, like if we have sufficient capacitor bank, okay, that will suffice our full um, uh, inductive load presence at the building, then we can able to maintain unity power factor. If we maintain unity power factor in this scenario, so our kilowatt is equal to kVA. So 3115 is our kilowatt, divided by 1 is the same, 3115 kVA is our new MD. So MD has been reduced from 3500 kVA to 3115 kVA by improving power factor from 0.89 to 0 unity power factor. So 3115 kVA is below our billing demand 3188 kVA. Okay, so we need not to pay additional demand charges since we are within the limit of billing demand. Okay, so while surrendering the contract demand, if we really don't want to keep the very little buffer, if our billing demand is 3188, it is very difficult, like if you feel like very difficult to operate power factor maintain 0.89 99 or 1 unity power factor. If you want furthermore buffer, you can always have a choice of surrendering back EB reduction of instead of 25%, you can able to plan to surrender 10 to 15% of contract demander back to EB. Okay, so let's take one more example or one more scenario. Okay, so I already told you we will be discussing on more case study. So for your better understanding how our demand charges will be, how our contract demand versus power factor will be, so how to optimize energy and how to maintain our maximum demand within the limit. So we will be I mean doing more case studies for better understanding. So let's go for last case study, scenario 3. Whether the, I mean in this also same, if you take like 5000 kVA is our contract demand and BD is 85%, but here the average maximum demand is 4500 kVA. Okay, and the building is operating at 0.93 power factor. Okay, so our building demand will be 85% of CD, that is 4250 is our building demand. So already our maximum demand crosses building demand. Okay, our billing demand is 4250, but our maximum demand already crossed to 4500. But we have a power factor of 0.93. Okay, so in this means still we have a feasibility to increase our power factor from 0.932 all the way unity power factor to reduce our maximum demand to make it less than our billing demand, so that we should not pay additional billing demand because of we crossed billing demand. So to avoid additional demand charges paid in this scenario, so what if we improved power factor from 0.93 to unity? Let's calculate. So before that, let's calculate the kilowatt. So kilowatt is equal to kVA into power factor. So our maximum demand is 4500 kVA operating at 0.93 power factor. So our building load in kilowatt is 4185 kilowatt, that is 4.2 megawatt almost. Okay, so next is to check desired power factor. Power factor is equal to kilowatt by kVA. So 4185 is our kilowatt and our billing demand is 4250 kVA. So 4185 divided by 4250, it is 0.99. So in this scenario, the desired power factor is 0.99. Okay, so but we are operating at 0.93. What if we improve our power factor from 0.93 to 0.99 or unity power factor? What is the impact? So let's check. So if we improved our power factor from 0.93 to 0.99 or unity, so then our new maximum demand in kVA will be 4185 kilowatt divided by 0.99 power factor, that is 4227 kVA. So that is less than our 4250 kVA billing demand. So we have reduced our maximum demand from 4500 kVA to 4225 kVA and avoided additional demand charges paying to EB. Okay, so from 4250 to 500, additional 250 kVA demand charges we paying to EB, that has been avoided because our demand charges has been reduced from 4500 kVA to 4225 kVA, which is lesser than our billing demand 4250 kVA. What if we improve to unity power factor? So our kilowatt is 4185 kilowatt. If it is unity, kilowatt is equal to kVA. So 4185 is our new maximum demand, so that is less than 4250 kVA. So in this scenario, okay, so instead of getting additional contract demand from the BESCOM, because we already reached our billing demand 4500 kVA, against the billing demand 4250 kVA. So BESCOM will give, EB authority will give you the letter to increase the contract demand. So instead of going additional contract demand increasing, so if you know your power factor is 0.3, by improving power factor from 0.93 to 0.99 or unity power factor, you making maximum demand come down from 4500 kVA all the way to 4225 kVA if it is 0.99 and 4185 kVA if you maintain unity power factor. Okay, so the demand charges paying to EB can be easily saved by improving power factor from 0.93 to 0.98 to unity power factor. Okay, now let us discuss about power triangle. Since we are discussing about power factor, okay, and improvement, okay, let us discuss about power triangle and base touch on causes of low power factor in common building infrastructure. Okay, so let's start with the power triangle. So this is the power triangle. Okay, in this active power is kilowatt, and that is OA from O to A, and the reactive component is A to B. Okay, that is KVAR. Okay, and our capacity apparent power is KVA is here OB. Okay, this is called power triangle, and kilowatt to KVA. So the angle between phase angle between kilowatt to KVA is 5, that is cos 5 power factor. Okay, so that is why power factor is equal to kilowatt by KVA. Okay, so key point in this what we need to know is like active and reactive power are right angles to each other, so it is right angles to each other, and kVA square, okay, this kVA square OB square is equal to OA square plus AB square. Okay, that is kVA square is equal to kilowatt square plus kVAR square. So in this one point you always keep note, kVA is the rating and capacity of the equipment. It is always higher than kilowatt. Okay, so kilowatt is our building load, the useful consumption by the utility assets, and kVA is a reactive component. Okay, so which is added up to the kilowatt. Okay, so adding reactive power and active power gives you the capacity or rating of equipment in kVA. Okay, so kVA is always higher than kilowatt. So kVA square is equal to kilowatt square plus kVAR square. So if there is any no loss, okay, no KVAR, there is no loss. It is practically impossible, no loss. Okay, then only our capacity will reach the KVA. Okay, so that is why. So if you maintain low power factor, okay, then your KVR reactive component will avoid the usage of your active component kilowatt. Okay, so friends, just this formula you please keep in your head, because in the next derivation, okay, for KVAR calculation, we may use we are going to use this formula. KVA square is equal to kilowatt square plus KVR square. Okay, so next key point is power factor cos phi is equal to OA by OB, that we already know, active power divided by apparent power kilowatt by kVA. And the next point is the lagging reactive power is responsible for the low power factor. Yes, because of this reactive component. Okay, so our phi is depends. So this our phi is different. So reactive component is a major responsible for our low power factor or power factor variations. Okay, and it is clear from this triangle that smaller the reactive power component, higher the power factor will be. So then our KVR calculation will be kilowatt into tan phi. Okay, this is also very important. In future slide for calculation we may require this formula as well. Okay, the reactive power is neither consumed in the circuit nor it does any useful work, and in wattmeter also it is not going to record kVARH. Okay, so uh, it is present, will be there, it is circulate here and there, but it is not useful for any of the work. Okay, and even your our trivector meter or wattmeter, it is not recording kVARH. Okay, so next goes to causes of low power factor. So most of our AC induction motors are low lagging power factor. It is working. The motor works at power factor which is extremely small. Okay, very small. Like in a light load, like it is working at 0.2 to 0.3 lagging power factor. And if you load more, then it may up to goes to 0.8 to 0.9 at full load lagging power factor. So now think, if induction motor loaded only 40%, 30%, it is working at 0.4, 0.5 lagging power factor, then assume how much KVAR capacitance reactance is required to neutralize lagging effect in power. Okay. So next is on our arc lamp, electric discharge lamps, and industrial heating furnaces, and most of the industrial purpose. So those equipments also operating at low lagging power factor. Um, so this is also one of the cause of having power working with the low power factor. And last is the load on the power system is varying. Okay, again, we all know like load shedding, like during morning and evening, and very high demand, okay, usage, and very low during other times, like afternoon and late night, the demand will reduce. Okay, due to these variations, there is a voltage uh, disturbance. Okay, for this it is going to create a magnetizing current. So that magnetizing current also decreases the power factor. So the load pattern variations also a reason of uh, low power factor. We have discussed the causes of low power factor. So now let's discuss disadvantages of uh, low power factor. So the major disadvantages of low power factor is a larger KVA rating equipment. As we said, like power factor is inversely proportional to KVA. If you keep on reducing, I mean, operating in low power factor, obviously you require larger KVA of rating of capacity of equipment to mitigate or to suffice your required active power kilowatt. So it will increase, low power factor will increase the requirement of KVA. Okay, this is because it is inversely proportional to power factor. And the second card is you required a greater size of conductor. This is why, because like kVA is directly proportional to current, voltage is constant, root 3 is constant. If you go with higher rating of kVA equipment, so obviously current requirement is, I mean, current consumption will increase. So obviously if you are installing higher capacity or higher rating equipment, obviously required conductor size is also high. Next, copper loss. Again, like if the equipment rating is high, conductor size is high, again the copper loss, I square R losses will be present. That is also leading higher power consumption. And poor voltage regulation. Already we discussed the variation in power factor will give you the various voltage drops. If the current is obviously some normal level, if you increase the rating, current is high, then voltage drop is also is going to increase. And reduce handling capacity of the system. Again, KVR will prevent the use of full load capacity utilized. So the kilowatt consumption you can't able to use maximum KVA rating capacity until unless you increase your power factor, because at unity power factor your kilowatt is equal to KVA. To the fullest capacity you can utilize the current consumption kilowatt in unity power factor only. Okay, so let's take very simple example on a single phase induction motor. Okay, whether this scenario, if we operate in low power factor, whether really the current consumption will go high or low. Let's take very simple example of one single phase AC motor. Okay, which is running 10 kilowatt, the full load, and the voltage level is 250 voltage, single phase. Okay, so then if it is operating at unity power factor, the input load current will be load current I will be P is equal to VI cos phi. There's no root 3 because it is single phase. and I is equal to P divided by V into cos phi. So 1000 divided by cos phi is unity 1. So third 10,000 10 kilowatt 10,000 divided by 250 voltage, it is 40 amps. Okay, if that single phase AC motor is operating unity power factor, 40 amps is the full load current. Okay, now let's check if it is operating at 0.8 power factor, then KVA it is itself is increased. Okay, because power factor is equal to kilowatt by KVA, then KVA is equal to kilowatt by PF. So KVA is equal to 10 kilowatt divided by 0.8 power factor. 10 divided by 0.12.5 KVA. Okay, so the current input is now P divided by VI cos phi, P divided by terminal voltage V, 12,500 kVA divided by power divided by 250 is equal to 50 amps. Okay, so obviously if the power factor is low, the required current at full load is become 50 amperes. Okay, the current 50 amps instead of 40 ampere. So obviously the conductor size will increase, copper losses will increase. Okay, so this is a scenario. These are very disadvantages if you are operating in low power factor. Okay, so let's take what is the improvement we'll get in a transmission losses if you improve the power factor from 0.8 to 0.95. Okay, if you improve the power factor, then obviously uh, the capacity will come down. Okay, because kVA is inversely proportional. If you improve the power factor, kVA will reduce. If the kVA rating is reduced, obviously the losses, the current requirement will reduce, the losses will reduce. So what is the percentage of reduction which will happen in a distribution and transmission and distribution losses reduction in the dead end, tail end power factor, tail end in the sense field end. Okay, like UPS output power and input power to the chillers. Okay, if you maintain 0 point instead of 0.8, 0.95, what if you improved 0 point power factor from 0.8 to 0.95 at your end stage? So what is the distribution loss we can save is percentage distribution losses is equal to 100, 1 minus power factor 1 divided by power factor 2 whole square. Okay, power factor 1 is 0.8 earlier. If you improve to 0.95, power factor 2 is 0.95. That is 1 minus 0.8 divided by 0.9 whole square. So that is 0.29, 29. If we improve our power factor from 0.8 to 0.95, 29% of our transmission and distribution losses can be saved. So that is why it is very important to maintain our power factor at a desired level. Okay, so not unity power factor always. Okay, optimum power factor which the building needs based on the building load. Okay, we need to calculate desired power factor and we need to maintain. If it is very less desired power factor, then obviously you may plan to surrender some contract demand if you don't have any future plan of expanding or adding additional load to the building. So far we have discussed causes of low power factor, disadvantages of low power factor. So let's discuss and derive how to improve power factor. Okay, and some calculation. So additional how much KVAR capacitor required for to improve the power factor. So these are some calculation recordings which I updated, which you'll see later. And in the method of improving power factor, there are three distinct methods. So first is to add a static capacitor. So those capacitor will take a leading current and that will improve our power factor by neutralizing the lagging effect in power. So, and the second is synchronous condenser. Okay, So synchronous motor running with the leading power factor, simply they will connect it to the grid. Okay, to improve the power factor, it is mainly on receiving station, substation areas. Okay, so next is on phase advancers. Okay, so mainly used in factories where huge induction motors, huge capacity induction motors, which are running with a very low power factor. uh, Adding this phase advancer will shift the phase angle between voltage and current, that will improve the power factor. These are the three distinct methods where we can improve the power factor from low power factor required or desired power factor. So in this, the first method, so adding capacitor, static capacitor along with the APFCRE relay, automatic power factor controller relay, is what we are using in our building or facilities to improve the power factor. Okay, so let's take one scenario, one building which is operating 2.8 megawatt load, and the power factor is 0.94, what they are maintaining with fullest. So they are turning on all the capacitor banks. So finally the 2400 kilowatt capacity power factor is 0.94 they are achieving. But now they wanted to improve their power factor from 0.94 to 0.99. Okay, so what is the additional KVAR capacity of capacitor is required, KVAR capacity is required to improve the power factor from 0.94 to 0.99. In this, there are two methods, okay, for calculation of additional KVAR required. So let's discuss about first. So it is simply like additional KVAR is equal to kilowatt into tan of cos inverse of power factor 1 minus tan of cos inverse of power factor 2. In this above scenario, so our kilowatt is 2800 kilowatt, and tan of cos inverse of power factor 1 previous, I mean what currently maintaining 0.94 minus tan of cos inverse of what exactly we required additional improvement is 0.99. Okay, so in this formula we can able to get additional KVAR required. So let's start play. It is 0.94 cos inverse tan of cos inverse 0.94 value 0.3629. Next is 0.99 cos inverse of 0.99. Tan of cos inverse of 0.99 is 0.14249. So next is 2800 kilowatt bracket into 0.36295 minus 0.14249 is equal to 617. So 2800 into 0.3629 minus 0.14249 is equal to 61 kVAR. So additional 617 kVAR capacity of capacitor bank, which we need to add up in the building to improve the power factor from 0.94 to 0.99. Okay, so let's go to another method of calculation. So earlier I said like one formula is there, kVA square is equal to kilowatt square plus kVAR square. Okay, so that formula, in that formula also we can able to derive what is the additional kVAR required to improve the power factor. So let's go to second calculation, option 2 calculation. Okay, so kVAR volt, okay, so is equal to, so kVAR in that formula if you derive, I mean kVA square is equal to kilowatt square plus kVAR square. So if we convert that for kVAR, then kVAR square is equal to kVA square minus kilowatt square. Okay, So if we remove square from KVAR, so then KVAR volt is equal to square root of KVA volt square and kilowatt square. So that is square root of 2800 divided by 0.94, because 2000 kVA is equal to kilowatt by PF. Okay, so 2800 divided by 0.9 whole square minus 2800 square. Okay, so let's go to this calculation. Square root of 2800 divided by 0.94 whole square minus 2800 square, close double bracket, then it is equal to 1016.26. So 1016 kVAR capacitor bank already there. Okay, so that is giving you 0.94 power factor. That is a power, I mean KVAR capacity of capacitor bank already available. Okay, so next is KVAR new. What is the KVAR new? To improve power factor from 0.94 to 0.99. So what is the KVAR which is coming? Okay, let's calculate. So 2800 square root of 2800 divided by 0.99 whole square minus 2800 square. That is coming 398.97 kVA. Okay, so additional kVAR required is 1016 kVA minus 399 kVAR. So 1016 kVAR minus 399 kVAR, that is equal to 617 kVAR. So in this method also, so we have achieved, so additional kVAR requirement is 617. In this method also we have obtained additional kVAR required is 617. So these are the two distinct methods where you can check the additional kVAR required for existing capacitor bank available, okay, to improve the power factor from one level to another level. Thanks for watching this video. Hopefully this video is informative. Okay, so if you have any doubts and clarification, please do comment. Once again, thank you for watching this video. Please subscribe and share. Please share this video to your friends and colleagues who is working in technical field. Hopefully it is helpful for them, okay, to understand their facility and building pretty much well, and to operate in optimizing energy consumption level to save more energy. Okay, so in this world, knowledge is wealth and sharing is caring. Please subscribe and share. Thank you so much.